Good morning, students. So today's class we are going to study about the time series model. Actually, for what purpose this time series model is used? Mostly for analyzing the non-stationary signal. So when do we call that signal? When we say that signal is said to be stationary, when the statistical characteristics of the signal does not changes with the time, we call it as a stationary signal. And if the statistical characteristics of the signal changes with varies with the time, then that means the input output characteristics of the signal varies with the time, we call it as non-stationary signal. So mostly this non-stationary signals, it can be analyzed using this time series model. Okay, so suppose if you have a non-stationary signal, how we can able to analyze it? We need to convert the non-stationary signal into a stationary signal. How do we convert this non-stationary signal into a stationary signal? We used to divide the signal into different segments. Then each segment we have to take it and then compute the and extract the signal, eliminate the noise and extract the signal from it. Okay, so there are so many techniques available. These time series models as parametric modeling techniques. So we'll be analyzing the signals in terms of parameters so that we model the signal as a parameter and noise also as a parameter, and we have to eliminate it. Okay, and any kind of signal, it is very important to apply the sampling process. How we can able to apply the sampling process? When we can convert the continuous signal into a discrete set of signals by applying t equal to n into capital T, where capital T is nothing but it is the sampling period. So we'll be dividing the continuous signal into equal intervals of time. How? Based on the formula t equal to n into the sampling period. Okay, so now we have a set of signals which is called S of t. When it is multiplied by the impulse function, del of t is an impulse function. According to the impulse function, it is defined as it is 1 for t is equal to 0, and other than t not equal to 0 for any positive points or negative points, it is 0 only. Now, this when the t is equal to kt, here t is equal to kt. So in that case, it will be delta 0. At 0, t equal to 0, you have the value as 1. We will be getting the signal as S of t. So this is generally, it will be, this is how the sampling is continue. So now, how we can model the signal? So this is the transfer function of a signal and the noise model. Okay. So we are getting the transfer function as B of Z inverse by A of Z inverse into U of Z. This is considered as a signal. And D of Z inverse by C of Z inverse into N of Z, that will be considered as a noise model. Now, this A of Z inverse, B of Z inverse, C of Z inverse and D of Z inverse, these are called as operators. Okay. So now this A of Z inverse, when we define this operator, it is expressed as summation I equal to 0 to P AI into Z power minus I. This P is called order of the filter. So here we can keep the I equal to 0 means A not equal to 1, that we can assume it. Similarly, for B of Z inverse, we can define as summation I equal to 0 to Q. Q is the order. Bi into Z power minus I. Like that, C of Z inverse, we can define summation I equal to 0 to N Ci Z power minus I. Like that, D of Z inverse as summation I equal to 0 to M Di small di Z power minus I. So this is how we can define the signal parameters model and noise model. Now, after that, the observation signal is S of Z equal to Y of Z plus the noise, signal plus noise. Signal is expressed as B of Z inverse into U of Z by A of Z inverse. When you cross multiply this equation, we call it as a deterministic system. Deterministic means the signal is already determined. This is the shape and this is the characteristics, like that. It is determined mathematically also. And in the case of Xi of Z, this is called as a noise. And when the Xi of Z is multiplied with Z of Z inverse, this is equated to D of Z inverse into N of Z. So this we call it as a noise model. When you draw the diagram of it, the bottom one, U of k multiplied by this transfer function, which is called a signal model, and N of k multiplied with this transfer function, which is called noise model. Both are added up in the adder, and this will give you the observation signal, which is called as S of k. Okay. So now in the time series model, we will be considering the signal as a signal plus noise, and we have to extract the signal from the noise. That is our ultimate aim. When the signal is buried with the noise, we have to extract from it. So now we have four different types of time series model. Those are ARMAX, which is called auto-regressive moving average exogenous model. Second one called ARMA, which is auto-regressive moving average model. Third one is AR, which is auto-regressive model. And fourth one is MA, which is moving average model. So these are the four different time series models are available. So one by one we are going to see. According to the Armax model, we have taken the observation signal. According to the observation signal, the first part is the transfer function of the signal. Second part is the transfer function of the noise. Okay. So now we are going to assume the denominator expression C of Z inverse. It is equivalent to the denominator of the signal A of Z inverse. So after using this assumption in this observation signal, at the denominator we are placing A of Z inverse in the noise model also. Now, after placing this, A of Z inverse is common in both signal and noise. This is being multiplied with S of K, S of Z. So once it is multiplied, we will be getting this equation. Now we have to apply the operators, define the operators here. So S of Z will be as such. And for A of Z inverse, when you define the operators, it is summation I equal to 0 to P, AI, Z power minus I. So this is equivalent to B of Z inverse. When you define the operators, it is summation I equal to 0 to Q, BI, Z power minus I into U of Z plus summation I equal to 0 to M, DI, Z power minus I, N of Z. So this is the equation you will get. Now, we are going to substitute I equal to 0 in this expression. When you substitute I equal to 0, it will be A naught into Z power 0. We know that Z power 0 equal to 1 and A naught also it is equivalent to 1. So that's why it is 1, it's substituted here. Plus, since it is a summation symbol, we are putting plus. Next, you have to substitute A1, 1 here, I equal to 1 here. When you substitute, it will be A1 Z power minus 1 plus A2 Z power minus 2, etc. So we can express it as summation I equal to 1 to P AI Z power minus I. And then this expression remains as such. Same thing we are putting it here. Now after that, we can multiply the S of Z with this expression and then only keeping the S of Z alone in this left hand side and bringing this term AI Z power minus I into S of Z term to the right hand side. It becomes a negative expression. So this is the expression we will be getting. So to this expression, when you apply this Z transform, if it is Z inverse of S of Z, it is called S of N minus 1. And Z power minus 2 of S of Z, it becomes S of N minus 2. So similarly, when you apply the inverse Z transform for these equations, you will be getting S of n equal to summation I equal to 1 to P AI S of n minus I plus summation I equal to 0 to Q Pi U of n minus I plus summation I equal to 0 to M Di n of n minus I. So this is called Armax model. Okay. So this is the final transfer function of an Armax model. Now let us move on to the next model, which is called ARMA model. So according to the ARMA model, again we have taken the observation signal in which the first part is the signal part, second part is the noise model. Here the assumption is there is no external noise. That means the second part of the equation becomes totally zero. That means we are eliminating the noise itself since there is no external noise. Now the equation becomes S of Z equal to D of Z inverse by C of Z inverse into U of Z. In this, the denominator term C of Z inverse, we are equating with A of Z inverse. This is like an assumption. So when you substitute A of Z inverse in the bottom denominator, you will be getting this expression as S of Z equal to B of Z inverse divided by A of Z inverse into U of Z. Now when you cross multiply the A of Z inverse with S of Z, and then if you define the operators, substituting the defining the operators in A of Z inverse and B of Z inverse, and then expanding it, we will be getting the equation as S of Z plus summation I equal to 1 to P AI Z power minus I into S of Z. This is equal to this term. I am keeping the S of Z alone in the left hand side and bringing this term AI Z power minus I into S of Z to the right hand side, it becomes negative. So when you apply the inverse Z transform, we'll be getting the equation for ARMA model as minus summation I equal to 1 to P. AI is S of n minus I plus summation I equal to 0 to Q. Bi U of n minus I. So this transfer function, we call it as ARMA model. So here the assumption is the external noise is absent. So here what are the parameters we are going to extract? The AI parameters and BI coefficients. So these are the parameters we are going to extract from the ARMA model. Then the next model is AR model. This AR model, we call it as all pole model. Again, we are taking the observation equation. We are making the external noise completely zero. And then this denominator term Z of Z inverse equal to A of Z inverse, and the numerator term B of Z inverse we are equating with the gain G. Now this equation becomes second half is completely zero. In the first portion we have certain assumptions. According to that assumptions, S of Z equal to G divided by A of Z inverse into U of Z. Then you just cross multiply with this, expand this, define the operator, expand this, and then bring this term to this right hand side, apply the inverse transform, you will be getting S of n equal to minus summation I equal to 1 to P AI S of n minus I plus G into U of n. So this is called AR model, or we can call it as all pole model. Next one. So the next case is MA model. We call it as all zero model. Again, you take the observation equation. It contains the signal plus the noise transfer function. In that the second term is completely zero. Since external noise is zero, then take the first term alone. In the first term, we are assuming that the denominator term C of Z inverse, it is equivalent to A of Z inverse. Then again, the A of Z inverse, it is equivalent to 1. So in that case, we don't have any denominator coefficients. We have only the numerator coefficients. Now, the S of Z is equal to B of Z inverse into U of Z. Now, you just expand or define the operator. If you define the operator, it is summation I equal to 0 to Q, Bi Z power minus I, U of Z. Now, in this, when you apply the inverse Z transform, you will be getting S of n equal to summation I equal to 0 to Q Bi U of n minus I. So, this is the MA model transfer function. Okay. So, in this class, in this time series model, we have studied 4 different models. One is ARMAX model, which is auto-regressive moving average exogenous model. ARMA model, which is auto-regressive moving average model. Then all pole model or auto-regressive model, which is called AR model. Then moving average model or all zero model, which is called as MA model. So in each model, we will be extracting certain parameters. So what is the parameters which is extracted in MA model? That is the B coefficients. What is the parameter which is extracted in the AR model? That is A coefficient. AI coefficients will be estimating it. What is the parameter which you are going to extract in the ARMA model? Which is AI coefficients and BI coefficients. What is the parameter when you extract in the ARMAX model? In that, since the noise is also present, we are going to extract AI, BI and the DI parameters, the signal plus noise parameters also. So this is how we do the modeling the signal and the noise, and our ultimate aim is to extract the noise or extract the signal which is buried in the noise. Okay, and we have to completely eliminate the noise and extract the signal. So that is an ultimate aim. So this time series models applications is it can be used in analyzing the EEG signal, because EEG signal mostly it is non-stationary in nature. So that's why this EEG signal for analyzing the EEG signal, this time series model is used. And how do we analyze the EEG signal when a non-stationary signal? You need to convert the non-stationary signal into a stationary signal by dividing the signal, non-stationary signal, into different segments. Then to the each segments, we can apply filter or something to extract the signal and eliminate the noise. So this is the concept of this time series model. Okay, hope you understand this derivations. So it is very simple and easier. Okay, so thank you all of you for watching.